Okay, so, we've been talking about this one for a while, and let's just dive right into it. The title of this research paper, and I'm just going to say it up front, Averages of Arithmetic Functions over Polynomials in Many Variables.
Okay.
Like, it's a mouthful, right?
Yeah, it's not the catchiest title.
Not something that you, pick up for a light read, But the good stuff, the really good stuff is often hidden, kind of like that.
It is. It's like a little treasure. You got to dig down deep to find it.
Exactly.
And this one, it really is a fascinating area of number theory. And, might sound intimidating, but it's about predicting patterns in numbers.
Yeah.
And that's something that has huge implications.
Ooh, I am intrigued already. So before we get into the really, complex stuff, can you just give us a little bit of refresher? What are arithmetic functions?
Yeah, absolutely. So think about it like this. You have a big Lego structure.
Okay.
Arithmetic functions are kind of like the individual Lego blocks.
Gotcha.
They're like the building blocks of, bigger mathematical concepts.
Right.
So a good example is prime numbers, right? Those are numbers that are only divisible by 1 in themselves.
Okay.
And they're super important in things like online security and all kinds of stuff.
Yeah.
So those arithmetic functions are the foundation.
Right.
And from there, things get really interesting.
Okay, that makes sense. So then where do polynomials fit into all of this? I vaguely remember them from, high school math class. But
It's been a while.
It's been a minute. Yeah, exactly.
No, polynomials, you can think of them as equations that basically define different shapes, curves.
Okay.
So if you think about an architect who's designing like a curved roof on a building,
right,
they might use polynomials to get that perfect arc.
Oh, okay.
They're kind of everywhere in mathematics, and they have applications in engineering, computer graphics, all sorts of fields.
So this paper then is looking at those polynomials and finding a way to predict the patterns within them.
Yeah, in a way, that's a good way to put it. So what they did is they developed this new theorem.
Okay.
And this theorem allows them to estimate the average of these arithmetic functions, but specifically over polynomials that have lots of variables.
Okay. So when we say lots of variables, more complicated than just your average everyday polynomial.
Exactly.
Gotcha.
Yeah. And it's like having this almost like a statistical superpower where you can look at these really complex sets of numbers and kind of get a sense of the overall behavior.
Okay.
Just by understanding how these averages work.
And that's a big deal to be able to have that kind of insight.
It is a big deal, yeah, because it can unlock a lot of things. But, I do want to mention there are some limitations here.
Okay. Yeah. What are we talking about?
So when we talk about these simpler polynomials, this theorem doesn't directly apply in those cases. It's really specifically for those polynomials with many variables.
Gotcha. So not a one-size-fits-all solution, but still a big step forward in terms of understanding how these patterns actually work.
Yeah. It's like we found this new tool,
right?
And it's really powerful for a specific type of problem.
Right.
And that's really exciting because this predictive ability, that has real-world applications.
Oh.
Things like cryptography.
Okay, let's unpack that a little bit. I always find cryptography fascinating because it feels so cloak and dagger and secretive and all that.
Right.
But it's also math. So how does this play into that?
Yeah, so one of the things that this paper looks at is something called the hasp principle.
Okay.
And basically it's asking, if a problem has a solution in one number system, does it automatically mean it has a solution in a different number system?
So it's does the rule apply across different mathematical languages almost?
Exactly. That's a great way to put it. And what's really interesting is that this paper actually proves that the hasp principle holds true for a very specific type of polynomial equation.
Okay. And that might seem small, but it's actually huge.
It is. Yeah. It's like, imagine discovering a new law of physics or something like that.
Right.
It may not have immediate everyday application, but it fundamentally changes our understanding of how things work at a deeper level.
Okay.
And that's what this is doing for this area of mathematics.
So it's like we're finding a missing piece of this giant puzzle. It might not be the whole picture yet, but it's getting us closer.
Exactly.
Okay, like that. And, it's interesting because this paper...
It doesn't just look at these grand principles like the Hasp principle.
Okay.
It also gets into the weeds a bit.
Oh, okay. How so?
So it provides us with new tools to estimate how many solutions exist for certain types of equations. And this has huge implications for cryptography, for example.
Because like more solutions, more possibilities when you're trying to create those like super secret codes.
Exactly, yeah. So let's say you're designing a new encryption algorithm. These tools could help you estimate how many possible keys you could generate, which is a measure of how secure that algorithm is against attacks. The more possible solutions there are, the more secure it becomes.
That's wild. So really, it all comes down to the number of solutions that are possible, and that's what makes it harder to crack.
Exactly. So we're not just talking about theory here. This has real-world implications for keeping our information safe online.
Right, right. Okay. But it's not just cryptography. I feel like we could take these ideas and apply them to like lots of different fields.
Absolutely. Absolutely. And that's what's really cool. So we talked about online security, but think about things like, urban planning.
Okay.
Trying to optimize this, like traffic flow in a city, or figuring out the most efficient way to distribute goods and services. These mathematical tools can actually play a role in all of those things.
It's amazing to me how like we start with this, really intense, complex math, and then it ripples out and can have an impact on things that we don't even think about on a daily basis.
Well, connected,
Yeah.
Math is the language of the universe.
Yeah.
And the more we understand that language,
Right.
the more we can unlock its secrets.
It's kind of beautiful when you think about it like that.
It is. It's pretty amazing.
Okay. So we've talked about the Hasse principle. We've talked about cryptography. This paper goes even deeper, though, right?
It does.
There's something in here about the Chawla conjecture, and I got to be honest, that one like completely went over my head.
Yeah, the Chawla conjecture, now that's a big one.
It's
a famous unsolved problem in number theory.
Oh, wow.
And to really explain it, we probably need a whole other deep dive.
Right, exactly.
But basically, at its core, it's about trying to predict the behavior of a specific kind of function when you apply it to polynomials.
Okay. And this paper actually manages to, like, prove it.
Well, not the whole thing. It proves a version of it for a very specific type of polynomial. But even that is a huge deal.
Okay. So it's like finding, I don't know, like a rare artifact that tells us something about this, like, ancient civilization, but it's not the whole story.
Exactly.
But it's a clue. It's a step in the right direction.
Precisely. And it opens up a whole new avenue of exploration. Because now we know that, at least in this specific case, the Chawla conjecture holds true.
Right.
And that gives us a starting point to maybe tackle some of the other, more general cases.
So they didn't just stop there. They were like, okay, we did that. Now what?
Yeah, they're like, let's push the boundaries even further.
I like that energy. Okay, so what else did they get into?
So they also started looking at something called non-algebraic varieties.
Well, non-algebraic varieties. Now we're just getting fancy.
I know, right? But basically, it means we're not just talking about simple equations anymore. We're bringing in exponents.
Exponents, like 2 to the power of x and all that.
Exactly.
Okay, so we're getting more complicated here.
We are. But that's what makes it so interesting. It shows us that the findings of this paper have the potential to reach far beyond what we initially thought. It's like opening a door to a whole new world of possibilities.
And who knows what we might discover in there. All right, I am ready to dive deeper into this. Let's take a quick break, and when we come back, we'll unpack some of these more complicated ideas. Stay tuned. Okay, so we were talking about non-algebraic varieties, and I gotta admit, my brain's doing backflips trying to wrap itself around this.
Yeah, it's definitely getting into some more abstract territory. But the cool thing is that even though it sounds super complicated, it still connects back to this idea of solutions. Remember how we were talking about how this paper helps us estimate how many solutions certain equations have?
Yeah, like in cryptography, how many possible keys you can make?
Exactly. So these non-algebraic varieties, even though they involve exponents and stuff, they still have solutions. And this paper's findings could potentially help us understand and estimate those solutions too.
Oh, okay. So even though it's more complex, those core ideas from the paper still apply.
Exactly. It's like we've got this new tool that's pretty versatile. And it just shows how far-reaching the implications of this research could be. We might be able to apply it to all sorts of problems that we haven't even thought of yet.
That's what I love about this kind of stuff, right? It's like, yeah, we can talk about cryptography, but it goes way beyond that.
Oh, absolutely.
So what else can we do with this then, if we're thinking about those practical applications?
Well, remember we touched on resource allocation earlier. This paper, even though it might seem very theoretical, it actually gives us more accurate ways to estimate, well, anything that involves counting solutions. So in a practical sense, think about things like optimizing network traffic,
Okay.
making sure data flows as efficiently as possible, or even things like distributing goods and services.
So like logistics, making sure things get where they need to be.
Precisely. This kind of math underpins a lot of those optimization algorithms.
It's blowing my mind right now thinking about how this connects to like Amazon delivery times or something.
It's all connected. You'd be amazed how often these really complex mathematical concepts pop up in our everyday lives.
I'm starting to realize that. Okay, so we've talked about cryptography, we've talked about resource allocation, urban planning. What else? Is there more? Because this paper, like, it goes deep.
It really does. And one of the things that really struck me is how they tackle this thing called the Chowla conjecture.
Okay, that's another one where I'm like, wait, what? Can you break that down for me a bit?
Right. So the Chowla conjecture, it's this famous problem in number theory. It's been around for a while, and it's kind of a head scratcher.
Unsolved mystery kind of thing.
Yeah, exactly. And this paper, believe it or not, actually manages to prove a version of it.
No way.
Yeah. Now, it's not the whole conjecture, but they proved it holds true for a very specific type of polynomial.
Okay, so like a piece of the puzzle.
Exactly. And in the world of mathematics, that's a big deal. It's like a huge step forward.
Because it gives you somewhere to go from there.
Exactly. It's like finding a clue that could unlock a whole bunch of other mysteries.
I love that analogy. Okay, so they're proving conjectures, they're applying it to all these different fields. What else? Because I know there's more.
Right. So on top of all that, they start exploring what are called non-algebraic varieties.
Oh, okay. Every time I think I'm catching up, we're adding new terms. Non-algebraic, what now?
Varieties. It sounds really intimidating, but basically we're moving beyond just those simple equations.
Okay, simpler is good, but I'm intrigued.
We're bringing in things like exponents now.
Yeah.
Like 2 to the power of x, that kind of stuff.
Oh, okay, so we're like leveling up the complexity here.
We are. And that's what's really exciting, because it means that this paper's findings could have even broader applications than we initially thought.
It's like that ripple effect we were talking about before.
Exactly.
It just keeps expanding outward.
It does. And we don't even know how far it could go.
That's a little bit terrifying, but also really, really cool. Okay, I need a minute to process all of this. Okay, my brain is like officially fried.
Yeah, it's a lot to take in.
It's a lot. But I feel like we're getting close to something here.
I think so too.
It's like all these threads are starting to come together.
They are.
So can we bring it back down to earth for a second and talk about what this actually means? Like, I get the theory, I get the math, but how do we actually use this stuff?
Right. So let's take the Hasse principle again as an example.
Okay.
Because you asked earlier, like, how would proving this principle for a specific equation, how would that actually be used in cryptography?
Yeah, like, does that mean we can suddenly create, like, unbreakable codes?
Well, not exactly. It's not like a magic bullet or anything.
Right.
But it's more about refining our tools
Okay.
and understanding the building blocks. This paper gives us more accurate ways to estimate the number of solutions for certain equations. And in cryptography, that translates to a deeper understanding of how secure a particular encryption method actually is.
So it's more about analysis than, like, taking what we already have and making it stronger.
Exactly. It's like, you have a building, and this research helps us make sure the foundations are really, really solid.
Okay, I like that analogy. So it's not just about creating new stuff. It's about understanding and improving what we've already got.
Exactly. And that's huge because we're talking about the security of our information, right?
Right.
That's not a small thing.
No, absolutely not. And it goes beyond that, right? We talked about resource allocation, how this math can help optimize all sorts of things.
Yeah, absolutely. Think about like network traffic. The internet is basically built on these complex mathematical models.
Right.
And as more and more devices come online, we need more sophisticated ways to manage all that data.
Okay, so this is like the future of the internet, basically.
In a way, yeah. And then there's everything else, logistics, transportation, even things like personalized medicine.
Wow. Okay. I'm getting a little overwhelmed here.
It's a lot.
But in a good way. In a good way. It's mind-blowing to think about how all these different areas are connected.
That's the beauty of mathematics, though, right? It's like this universal language that underlies so much of our world.
And this paper is like giving us a new dictionary almost.
Yeah. Or a new grammar book, maybe?
Okay, I like that. It's helping us understand the language in a deeper way.
Exactly. And who knows what we'll be able to say with it in the future.
It's exciting. All right, well, I think we've all officially earned our PhDs in number theory.
At least honorary ones.
Right, exactly. So I think it's time for us to surface from this deep dive
Yes.
back into the real world. But hopefully, we've left you with a little bit of a sense of wonder
Absolutely.
about the power of math and all the amazing things that we can do with it.
It's truly remarkable.
It is. It is. All right, until next time, keep those brains buzzing, and we'll see you on the next deep dive.
Okay, get ready, because today we're taking a deep dive into the fascinating world of number theory with a paper on, get this, averages of arithmetic functions over polynomials in many variables.
Yeah, it's a bit of a mouthful.
It is. But it's actually way more interesting than it sounds. We're essentially trying to figure out how often certain kinds of numbers pop up when we use really complicated equations.
Imagine it like we're trying to find patterns, but instead of looking for them in like a picture or something, we're looking for them in numbers.
I like that. So to understand these patterns, we need to start with the basics. Can you remind us what exactly an arithmetic function is?
Oh, absolutely. So an arithmetic function, you can think of it like a machine, right? You put something in and it spits something out. But in this case, you put in a whole number, any whole number, and the arithmetic function, based on the properties of that number, spits out another whole number.
Okay, so like a prime number detector, for example.
Exactly. Like if you put in the number 7, it'll be like, yep, that's a prime number. But if you put in 10, it'll be like, nope, not a prime number.
Perfect. And in this paper, we're looking at how these arithmetic functions work within polynomials, but not just any polynomials, ones with a ton of variables, right? Why does that make it so tricky?
Well, imagine trying to bake a cake, but this cake has like 20 different ingredients.
Okay, that's a lot of ingredients.
It is. And each ingredient interacts with the others in all these complicated ways. That's kind of what it's like dealing with polynomials that have lots of variables. Each variable adds another layer of complexity, making it really hard to predict what's going to happen.
So how does this research paper tackle that challenge? What's their secret sauce?
Well, they've introduced 2 new theorems.
Okay.
And you can think of these theorems as like special tools. One of them is kind of like a mathematical compass, and the other is like a ruler.
A compass and a ruler. I like that.
Yeah, they give us a way to navigate through all that complexity and start to make sense of those hidden patterns.
Okay, so tell me more about these tools. What makes them so special?
Well, the first theorem, Theorem 1.1, it's all about figuring out how much we can trust our predictions. It's like having a built-in error detection system for these really complex calculations.
So even before you start working on a problem, you have a sense of how reliable your answer is going to be.
Exactly. Now, the second theorem, Theorem 1.2, that's our workhorse. This one actually gives us a formula to calculate the average behavior of these numbers, but with a catch. This formula only works if the numbers we're looking at are what we call equidistributed.
Equidistributed, that word again. What exactly does that mean? It sounds like something to do with balance.
You're right, it does. Think of it like this. Imagine you have a jar full of marbles, and you want to know how many of them are red. If the red marbles are all clumped together at the bottom, it's harder to guess how many there are just by grabbing a random handful, right? But if those red marbles are spread out evenly throughout the entire jar, then you have a much better chance of getting a representative sample.
So equidistributed basically means spread out evenly.
Exactly. And that's what makes these theorems so powerful. They give us a way to analyze those situations, even when things aren't perfectly balanced or evenly spread out.
Okay, so we've got our compass and our ruler, these awesome theorems that help us make sense of these special numbers. But how does this actually play out in the real world? What kind of problems can we solve with these tools?
Well, one really fascinating area is cryptography.
Oh, yeah.
Which, as you might know, relies a lot on the unique properties of numbers.
Right, like that code breaking idea we were talking about.
Yeah, exactly. One application is in something called Diophantine equations. And these equations are all about finding whole number solutions, which sounds kind of simple, but trust me, it can get ridiculously complicated.
So instead of just any solution, we're looking for those nice, clean, whole numbers.
Exactly. And that's where something called the analytic Hass principle comes in. It basically tells us that if we understand how these arithmetic functions behave on average, we can actually get clues about whether or not those whole number solutions even exist for a particular Diophantine equation.
So it's like getting a sneak peek into the equation's possibilities before you even start crunching the numbers.
Exactly.
Okay, cool. You also mentioned this research could be helpful in data science. How so?
Well, just think about it. Data analysis is all about finding patterns in large sets of numbers, right?
Right, finding those hidden connections.
Exactly. And these new theorems give us a fresh way to analyze how certain sets of numbers are distributed within a much larger set.
Interesting.
They can reveal those subtle little patterns, those correlations that we might miss if we're just using our typical statistical methods.
It's like having a superpowered magnifying glass for our data.
Mm.
I'm really seeing how versatile these tools are. But you also mentioned something about understanding the shape of objects that are, get this, difficult to even visualize. And that's where my brain starts to hurt a little bit.
Yeah, this is where it gets really mind-bending. This research actually has implications for understanding the geometry of something called non-algebraic varieties.
Okay, hold on. Before we go too far down the rabbit hole, what exactly are non-algebraic varieties?
Imagine trying to describe what a cube looks like to someone who's only ever seen the world in 2 dimensions.
Okay, so they've never seen anything three-dimensional.
Exactly. That cube exists in a dimension that they just can't fully grasp. And non-algebraic varieties are kind of like those cubes. They exist in higher dimensions than our brains are typically able to wrap themselves around. Our everyday geometric tools just aren't enough to describe them.
So you're saying that these new theorems can help us study these crazy shapes, even though we can't actually picture them in our minds.
Precisely. They provide us with a new lens to examine their properties, even if we can't directly visualize them. And what's even cooler is that they're not just limited to these obscure geometric shapes.
Oh, really?
Yeah. These theorems can also shed some light on more familiar mathematical concepts.
Like what? Give me an example.
For instance, prime numbers.
Okay.
They can help us understand how prime numbers are distributed within certain sequences generated by polynomials. It's kind of like discovering this hidden order within something that we originally thought was random. It's pretty remarkable.
That's amazing. Wow, we've covered a lot of ground in this deep dive. From like the very definition of an arithmetic function to the mysteries of higher dimensional shapes and the secrets hidden within prime numbers.
It's pretty amazing, right?
It is. This one research paper touches on so many different areas of math. It just goes to show how interconnected everything really is. So for our listeners who might be hearing all of this for the first time, what's the key takeaway here? Why should they care about these theorems and all their applications?
You know, it's easy to get caught up in all the technical stuff, but at its core, this research is about patterns and predictions.
Oh. And that's relevant to so many different fields.
That's true, from like cracking codes to analyzing huge data sets to even pushing the boundaries of what we know about the universe. It seems like these tools have the potential to unlock a lot of doors for us.
Exactly. And you know what? Like any good exploration, this research, it opens up even more questions. In fact, the paper even mentions this really intriguing unsolved problem in number theory called Chowla's conjecture.
Ooh, I love a good math mystery. What's the story with this conjecture?
Oh, it's a tough one. Mathematicians have been trying to crack this code for decades. But reading this paper with its new way of looking at arithmetic functions, it got me thinking. Could these new theorems hold the key to finally unlocking Chowla's conjecture? It's a long shot, but still pretty casing to think about. So this research might not only help us solve problems we're facing right now, but it could also pave the way for solving some of math's longest-standing mysteries. That's a pretty inspiring thought to end on.
It really is. It just shows you, even in a field like number theory, which can seem so abstract sometimes, there's always something new to discover.
Absolutely. And sometimes those discoveries can have ripple effects way beyond what we could have imagined.
Exactly.
Well, this has been a fantastic discussion. I always love these deep dives because it reminds us that even the most complex mathematical ideas, they often have these surprising connections to the world around us.
It's like we're seeing the world through a new lens.
Exactly. A huge thank you to you for guiding us on this incredible deep dive into the world of arithmetic functions. And to our listeners, until next time, keep those curious minds exploring because you never know what amazing connections you might find. Have you ever stopped to think about how numbers are, well, everywhere? I mean, they're in nature, they're in technology. It's kind of wild when you think about it.
Yeah, it's true. Numbers really are the kind of like the building blocks of, well, everything when you get down to it. And just like with any set of building blocks, there are tons of ways to arrange them. And some of those arrangements, well, they reveal these amazing patterns and connections.
And that's where number theory comes in, right? It's like we're trying to crack the code of the universe, and the code is written in numbers.
Exactly. And that's what makes this deep dive so fascinating. We're taking a look at a paper called, get this, Averages of Arithmetic Functions over Polynomials in Many Variables.
Okay, I'll admit that title's a mouthful, but I'm intrigued. Before we get too deep, though, can you remind us what a polynomial is? I think I might have blocked out some of my high school algebra classes.
Oh, sure. Think of a polynomial as just a fancy way of combining variables, like x or y, with numbers and exponents all strung together with plus and minus signs.
Okay, so like that old chestnut, x squared plus 2x minus 3, that's a polynomial.
You got it. That's a classic example.
Right, those guys. So this paper we're diving into today, it takes those polynomials and feeds them into these things called arithmetic functions. Now, I got to ask, what exactly are those and why are they so important?
So imagine an arithmetic function, kind of like a machine, right? You put a number into this machine, and based on certain rules, it spits out another number. For example, one simple arithmetic function tells you how many divisors a number has.
Okay, so like the number 6, you put it into the arithmetic function machine, and it spits out 4 because 6 has 4 divisors. 1, 2, 3, and 6.
You got it. You're getting it.
Okay, so now we're taking these polynomial machines that crank out numbers. We're feeding those numbers into the arithmetic function machines, and then we're averaging the final outputs. I have to ask, though, what's the big idea behind all this averaging?
That's where it gets really interesting. Destignol and Sophos, the mathematicians who wrote this paper, they found that when you average the outputs of these arithmetic functions over a bunch of numbers made by polynomials, bam, these really cool patterns pop up.
It's like those polynomials have a secret language, and by averaging, we're starting to decipher it.
That's a great way to put it. And to go even deeper, they use this really powerful tool from number theory called the analytic Hasse principle.
Okay, now you're just using big words to scare me.
No, it's not that scary, promise. Imagine you're trying to solve one of those really complex equations that could have multiple solutions.
Okay, I'm picturing one of those with a jumble of letters and exponents, the kind that used to give me nightmares in school.
Right, so the Hasse principle is kind of like looking at this equation from a bunch of different angles, like shining a light on it from all directions. If the equation has solutions in different mathematical structures or universes, then it's more likely that it'll have a solution in the real world, too.
So it's like we're checking for consistency across multiple dimensions to see if something holds true overall.
That's a great way to put it. And what Destignol and Sophos did was take that idea and apply it to polynomials.
So they're shining that multidimensional light on these polynomials to see how they behave in different mathematical settings.
You got it. And through that process, they started to reveal these hidden connections between equations that seemed totally unrelated before.
Wow, that's blowing my mind already, and we're just getting started. But from what I understand, this paper goes even further, right? They start exploring these complex shapes called non-algebraic varieties.
You're right, they do. They go beyond just looking at the numbers coming out of these polynomials. They're venturing into this higher dimensional geometry, using their findings to shed light on some really fascinating mathematical objects.
Okay, now you're making me really curious. But before we get lost in those multidimensional shapes, let's take a closer look at those hidden patterns and connections that Destignol and Sophos found using the Hasse principle.
So you remember how we were talking about the Hasse principle, like how it helps us figure out if an equation has solutions by, looking at it from all these different angles.
Right, like we're shining a multidimensional flashlight on these equations.
Exactly. So Destignol and Sophos, they applied this principle to this, it's kind of a tricky problem. It's like, imagine you have this multidimensional graph.
Okay, now we're talking about graphs. I can almost feel my high school math anxieties creeping back in.
Don't worry, these aren't your typical graphs. We're not talking about simple lines and curves here. Think more like, those crazy 3D models you see in sci-fi movies.
Okay, I'm trying to picture it. So these graphs are twisting and turning in all these crazy ways, but instead of being made of, spaceships and aliens, they're made of pure math.
Precisely. And these graphs, they represent these really complex things called non-algebraic varieties. They go beyond your typical equations because they involve these special functions.
Okay, so we're dealing with some seriously high-level math here. What exactly did Destignol and Sophos discover about these non-algebraic varieties?
Well, they figured out a way to use their work on averaging those arithmetic functions, the ones we talked about, to actually count specific points on these crazy graphs.
So they're zooming in on these multidimensional graphs and pinpointing specific locations.
Yeah. And get this, they're not just counting any points, they're specifically looking for points that have whole number coordinates.
Wow, that's some serious precision. It's like they found a way to impose order on something that seems utterly chaotic.
Exactly. And speaking of elegant mathematics, their research actually touches on a really famous unsolved problem in number theory it's called Chola's conjecture.
Oh, right. I've heard of that one. But to be honest, it's always seemed a bit, well, impenetrable. It's
Yeah,
about randomness.
you got it. It's about trying to prove whether some sequences of numbers are truly random, like the flip of a coin.
So it's like saying that there's no way to predict what number comes next in these sequences, no hidden pattern.
Exactly. And while they didn't solve the entire conjecture, that's a really tough one, they did manage to prove that it's true for numbers generated by certain polynomials with many variables.
Okay, so they're like chipping away at this massive mathematical puzzle piece by piece.
Exactly. It's often how breakthroughs happen. You start small, prove smaller cases, and eventually those little pieces start to come together.
I love that. It's a reminder that even in the face of these huge challenges, every step counts. Speaking of which, we've covered a lot of ground here, from those arithmetic functions to those crazy multidimensional graphs. Can you remind us why all this research matters in the, the real world? So I have to ask, this has been a fascinating deep dive, but some of this seems, well, pretty abstract. How does all this stuff about polynomials and number patterns actually, make a difference in the real world?
That's a question I think every mathematician grapples with. It's like we're in this world of theorems and proofs, but how does it connect to, real life? Well, it might surprise people to know that number theory, which seems so abstract, it actually pops up in some very unexpected places.
Okay, like where? What are we talking about here?
One of the biggest ones is cryptography.
Cryptography,
Yeah.
like keeping our online information safe.
Exactly. See, cryptography relies on finding patterns in numbers, but also on unpredictability. And the work we've been talking about, it gives us these new tools to understand both of those things.
So this research could actually lead to better online security.
It's definitely possible. And it goes beyond just cryptography. Think about computer science, like designing faster algorithms for data analysis or machine learning. These all rely on a deep understanding of how numbers behave, how they're distributed.
So by cracking the code of these polynomials and arithmetic functions, it could lead to more efficient computer programs.
Exactly. It might seem like a stretch, but that's the thing about knowledge, right? You never know where it might lead.
That's amazing. It's like we've been looking at all these individual gears and springs, and now we're starting to see how they all fit together to make a clock tell time,
I like that analogy. And the most exciting part is we're just getting started. There's still so much more to explore in number theory.
Like what? Give us a sneak peek of the next big mystery.
Well, we touched on Chola's conjecture, and that's still a big one. But there are tons of other questions about, say, prime numbers, or even more complex mathematical structures than the ones we've talked about today. It really feels like the exploration never ends.
It's like there's always another layer to uncover. That's pretty exciting.
It is. And who knows what incredible applications we'll find for these discoveries down the road. The possibilities are really endless.
Well said. A huge thank you to our expert for being such a fantastic guide on this deep dive into the world of number theory. And to all our listeners, thanks for joining us. Remember, the universe of numbers is full of surprises. Just keep exploring, and you never know what you might find. Hey everyone, welcome back. Ready to dive into something kind of surprising? We're tackling number theory today. But don't worry, it's way cooler than it sounds, promise.
It really is fascinating stuff.
We're going deep on a paper, essentially giving mathematicians a whole new tool set.
Oh, absolutely.
It's about figuring out how often these special numbers, pop up in equations.
Right, exactly. And that might sound a bit, well,
Little niche.
yeah, Dad. But think about it like this. Imagine predicting what kind of numbers will show up in a sequence. That's powerful stuff.
Big implications. From super practical things like cryptography.
Which we're definitely getting into today.
To, get this, maybe even music. To help us break it all down, we've got an expert in the house. Welcome to the show.
Thanks for having me. Happy to be here, really.
So the paper we're looking at is averages of arithmetic functions over polynomials in many variables. Catchy title, right?
Definitely a mouthful.
But it's about these special numbers that show up when we use certain types of equations, those polynomials.
Right, and I think maybe we should touch on polynomials just a bit, in case someone's hitting a flashback to high school algebra.
A little refresher never hurts.
Exactly. Imagine an equation, but it's got variables in it, like x or y equals 5, that kind of thing. That's your polynomial. A mix of variables and numbers all strung together with pluses, minuses, and multiplication.
Okay, so this paper is looking at how often certain numbers, special ones, show up in the results of those equations.
Exactly. But it's even more specific than just any special number. We're talking about a kind linked to arithmetic functions.
Okay, those sound a little intimidating.
Not really. Think of them like little machines. You feed a number in, it spits out another based on a rule.
So like if I put 12 into this machine, it might spit out 6 because 12 has 6 divisors. 1, 2, 3, 4, 6, and 12 itself.
Perfect example. And what's really cool is this paper doesn't just describe these patterns, it actually builds a tool to help us figure out why they exist. It even proves a really tricky math problem, Schole's conjecture, for a specific type of polynomial.
Which
A
is
smooth, homogeneous polynomial.
Okay, now that one definitely needs some breaking down.
Yeah.
For those of us who aren't, living in the world of math equations all day, what's the plain English version?
Okay, imagine something perfectly round and smooth. A billiard ball, maybe?
Okay, I can picture that.
A smooth, homogeneous polynomial has a kind of mathematical symmetry that's similar to that.
Interesting. So for those specific billiard ball polynomials, this research actually proves that Schole's conjecture is true.
You got it. Though, to be fair, Schole's conjecture is this really complex statement about patterns and sequences of numbers. What's amazing about this research is that it doesn't prove the conjecture in every case.
So there are still some mysteries out there.
Oh, tons. There are plenty of those billiard ball polynomials where it's still a puzzle.
But still, finding even one piece of that puzzle, that's a huge deal, right?
Absolutely. It's huge progress. And you know what's really interesting? This paper isn't even about solving those specific problems directly.
It's about the journey, not the destination.
In a way. It's about creating this new tool, this mathematical Swiss Army knife that helps us understand these patterns, these special numbers, in a whole new light.
Okay, now I'm really hooked. Give us an example. How does this actually work in practice?
Well, one of the key things they did was use something called Fourier analysis. Imagine listening to a whole symphony orchestra. You hear all those instruments, right? Creating this big, complex sound.
Right, a wall of sound almost.
Exactly. Fourier analysis, it's like having superhuman hearing. You can isolate each instrument.
Whoa, so I could pick out the oboe, even in the middle of everything else.
Exactly. You hear the violins, the trumpets, all separately, even though they're playing at the same time.
That's wild. Okay, so instead of sounds, these mathematicians, they're using Fourier analysis to break down these complex polynomials, like into their individual mathematical notes.
Exactly. They're analyzing how the polynomial's output changes as you tweak the input variables. It's like fine-tuning those instruments we were talking about.
Okay, so it's about understanding those individual parts, and then you can kind of predict the overall behavior. So they can predict how often those special numbers, determined by our arithmetic functions, will appear. Like they have a cheat sheet.
Yeah, exactly. It's like they know which notes to play, which variables to tweak to get those special numbers to pop up.
That's so cool. And you mentioned earlier this research, while it's in a pretty abstract area of math, could actually have real-world impact, especially in cryptography.
Oh, absolutely. Cryptography, at its core, it's all about finding functions that are easy to do in one direction, but super hard to reverse engineer.
So like a lock that's easy to close,
Right.
but almost impossible to pick without the key.
Exactly. And some cryptographic systems, they actually rely on prime numbers, right? Remember those arithmetic functions we were talking about?
Yeah.
Figuring out if a number is prime? Classic example of an arithmetic function.
Okay, yeah, I've seen the connection here. So if you use those prime numbers as your key, it'd be nearly impossible to crack the code without knowing those specific primes.
Exactly. And what makes it even stronger, the bigger those prime numbers are, the harder it becomes to factor them, which is what you'd need to do to break the encryption.
So in the context of this research, a good cryptographic function would be one where it's easy to plug in values for the variables, those x's and y's in our polynomial, and get an output but.
But incredibly hard to go the other way, to figure out what those inputs were just by looking at the result. Ideally, you'd want something so tough that even with like all the computers in the world, it'd take billions of years to reverse.
So that's where this mathematical Swiss Army knife comes in. This research helps us analyze those functions, see if they're up for the job of cryptography.
Precisely. It all comes down to this idea of computational hardness, which sounds really complicated, but
It's about how much effort a computer needs, right, to crunch those numbers.
exactly. How much work does it take to do the math? And in cryptography, you want it to be hard, easy to scramble the message, lock that lock, but almost impossible to unscramble it without the key.
So how does this research help us find those tough functions? What do they actually discover about how often these special numbers show up?
Well, they found that how often these special numbers pop up in the outputs of our billiard ball polynomials.
Right, our smooth, symmetrical ones.
Yes, it's directly related to which arithmetic function you're using and even the shape of the polynomial itself.
Okay, so it's not about finding one magic formula for cryptography. It's about the interplay between the polynomial and the arithmetic function.
You got it.
Mhm.
It's like a dance, a delicate balance. And the more we understand that dance using the tools this research gives us, the better we are at making those cryptographic systems super secure.
It's amazing how something as, I don't know, seemingly abstract as number theory can have this direct impact on something as practical as, like, keeping data safe.
Right. And it goes even beyond that even. Remember how we talked about Fourier analysis being like breaking down a symphony?
Yeah, the superhuman hearing thing.
Well, some mathematicians, they think these same ideas might apply to music itself.
Wait, are you saying math could help us create music?
It's a possibility, just like the patterns in a polynomial can determine how often you get those special numbers, the patterns in musical scales, harmonies, they might have hidden mathematical stuff going on too. This research, it's like opening a door to explore that even further.
That's wild. This has been such a fascinating deep dive. So to wrap things up, what are the key takeaways about this research?
I think the most exciting thing is that new mathematical tool they created. It's like we've been given a new lens to understand how numbers behave, and that's going to have impacts way beyond what we can even imagine right now, I bet.
A new lens. I like that. It's like
Okay.
we've just scratched the surface. So what's next? Where does this research go from here?
It's wide open, really. Like, think of any field where patterns matter. Computer science, data analysis, even physics. This research, it gives us a totally new way to look for those patterns and really understand them. It's exciting stuff.
So it's not just the numbers themselves, it's the tools.
Yeah.
And what those tools let us do in other areas.
Exactly. Remember how we were talking about this research, like maybe even helping design more secure cryptographic systems? Well, imagine those same ideas, but applied to something like, I don't know, artificial intelligence or machine learning. Instead of just, feeding data to an algorithm, we could use these tools to really get the math underlying all that data.
So we could potentially have AI systems that are not just like more efficient, but also way more secure, more reliable.
Exactly. And that's just one example. Who knows what other applications are out there that we haven't even thought of yet. That's the awesome thing about fundamental research. It's laying the groundwork for stuff we can only just start to glimpse.
It's like we've been given this map, but it's not for a place, it's for a whole new continent of ideas. And it's up to us to go explore.
I love that analogy. And the best part is it's not a physical space, right? We're exploring the world of math, which is infinite. There's something really wonderful about that, don't you think? That sense of discovery.
Absolutely. And who knows, maybe someday we'll listen to a symphony, but
Yeah.
it was composed using these same mathematical principles we've been talking about.
Wow, now that would be incredible. Really taking it full circle, a true testament to how powerful math can be and how beautiful, honestly.
Well, on that note, folks, it looks like we've reached the end of our deep dive for today. We've journeyed from these super abstract number theory ideas all the way to their potential to, actually shape the future. Amazing stuff.
It's been a pleasure, really. Thanks for having me. Always fun to talk about this kind of research.
And a huge thank you to all of you for joining us on this adventure. We hope you've come away with, I don't know, maybe a new appreciation for just how elegant math can be, how powerful it is, and, dare I say it, maybe even a little beautiful. So until next time, keep exploring those questions, keep those brains engaged, and keep looking for those hidden patterns all around us. You never know what you'll find.
Ever catch yourself looking for patterns in everyday life, like trying to find some kind of, I don't know, like a hidden order behind everything?
Well, get ready, because this deep dive is all about uncovering that hidden order. Mathematically speaking, at least, we're looking at averages of arithmetic functions over polynomials in many variables.
Okay, gotta admit that title's a mouthful.
Yeah, it's a bit of a tongue twister. But the idea is so cool. Imagine being able to predict, how often something happens even when there are tons of factors involved.
So like predicting how bad traffic will be during rush hour.
Exactly. It seems chaotic, but with the right tools, those hidden patterns emerge. But instead of cars on the freeway, we're dealing with something called arithmetic functions.
Uh-oh, does this require a math degree?
No, not at all. Just think of them as rules about numbers, like prime numbers, always a good time, right?
Or how many divisors a number has.
Okay, I'm with you. Prime numbers, divisors. So like the number 12 has 1, 2, 3, 4, 6, and 12 as divisors, which is 6.
You got it. You're a natural. And this paper is all about how these functions behave within polynomials.
Polynomials. Now we're really digging deep.
Haha, it's not as scary as it sounds. Think of a polynomial like a mathematical landscape with peaks and valleys. But instead of trees and rocks, we're mapping out where these arithmetic functions pop up. And get this, the paper focuses on a specific type of polynomial called a smooth form.
Smooth forms. That sounds suspiciously melodic for a math concept.
Maybe not melodic, but definitely elegant. Think of smooth forms as a controlled environment for our mathematical experiment.
So they make the math more manageable. Exactly. They have these really predictable properties, making it easier to study how averages behave.
Okay, so we're looking at how often things like prime numbers appear within these well-behaved, smooth forms. It's like we've got our own little mathematical laboratory, right?
That's a great way to put it. And to make things even more interesting, they use this clever trick called equidistribution to unlock even more insights.
Okay, now you're speaking my language. Equidistribution. It's like, imagine you're dropping jelly beans into a jar.
Now you're thinking like a mathematician.
So you're saying these mathematical jelly beans hold the key to understanding this paper. I'm hooked.
They're a surprisingly accurate analogy. Think about it. If you shake that jar of jelly beans just right, give it a good mix, they'll spread out pretty evenly, right? No giant clumps of just the red or the blue ones.
Makes sense.
That's equidistribution in action. Things naturally wanting to find that balance, that even spread.
Okay, so we're not just talking about averages anymore. We're talking about how evenly those averages are spread out. Like, within our polynomial, are the prime numbers all bunched up together, or are they spread out nicely?
Exactly. It's like each colored jelly bean represents a different arithmetic function, and instead of a jar, we have our polynomial space. And this paper looks at how this whole idea, equidistribution, can actually help mathematicians estimate the average values of these functions, but within certain areas of the polynomial.
I see. So we've got our averages, we've got this equidistribution thing going on, and it's helping us make sense of how these functions behave, how they're distributed within these polynomials. But like, what's the practical use of all this?
Well, that's the really exciting part. This might seem like purely theoretical math, but it actually has some really surprising applications. For example, it sheds light on something called the analytic Hasse principle.
Analytic Hasse principle. Definitely going to need a little help on that one.
Right. So basically, it's a way to figure out if certain equations have solutions that are, whole numbers, nice and clean, no messy fractions or decimals.
Because nobody wants to deal with a fraction when they're trying to solve an equation, right?
Exactly. And what these mathematicians have found is using averages and equidistribution, they can actually show that this analytic Hasse principle holds true, but for a very specific type of equation, ones that involve sums of squares.
Wait, so you're telling me we can actually, predict if an equation will have those nice, clean, whole number solutions?
That's exactly what I'm saying. It's like discovering a secret rule that governs a whole bunch of mathematical problems.
Okay, that's pretty impressive, I have to say. But is that all?
Oh, we're just getting started. This paper goes even further. It gives us the tools to actually count how many whole number solutions exist for certain equations. We're talking equations where one side is a power of 2 and the other side is a polynomial.
Now you're just showing off.
Well, let's just say these mathematicians have found some seriously elegant ways to tackle some really, really complex problems.
So we've gone from averages to being able to predict solutions to actually counting those solutions. Is there anything these ideas can't do? What about some of those big unsolved problems?
Funny you should ask that. There's this famous unsolved problem in number theory. It's called Cella's conjecture.
Cella's conjecture sounds ominous.
It's like the holy grail for a lot of mathematicians in this field. And get this paper. While it doesn't completely solve it, it makes some serious progress.
Wait, hold on. Are you saying they cracked the code on a legendary math mystery?
Well, not completely, but they made a huge dent. Imagine trying to climb Mount Everest. This paper gets us to base camp, but way higher than anyone's ever been before. They were able to prove Cella's conjecture, but only for a specific set of polynomials.
Okay, so not the summit, but still, that's a huge accomplishment.
Absolutely. A huge step forward, and it opens up all these new, exciting avenues for research.
So much for those unsolved problems. I mean, this paper's clearly a game changer. But I have a feeling there are more layers to this onion, right?
You know me too well. Remember those smooth forms we talk about? The really well-behaved polynomials this whole paper focuses on?
Yeah, our little math laboratory.
Well, imagine what happens when we step outside the lab.
You're gonna leave me hanging, aren't you? You're killing me. Okay, so what happens when we leave behind those well-behaved, smooth forms and venture out into the wild west of, other types of polynomials?
Well, that's where things get really interesting. You see, this paper, it focuses on polynomials with, like, a lot of variables.
A lot. Like, how many are we talking here?
Think, like, 100 balls in the air at once. It's that level of complexity. And their methods work beautifully in that setting.
Okay, so lots of balls, lots of variables, it all makes sense. But
It makes you wonder, right? What if we only had, say, 10 balls? Or even 5?
could we still find those hidden patterns, those surprising connections?
Now, that is the million-dollar question. It's like this paper, it's opened up this whole new continent to explore, right? We've charted a few landmarks, but there's this vast, uncharted territory out there.
So less of a finished map and more of a starting point.
Exactly. They've given us this incredible set of tools, these hints that there's even more out there. Who knows what we could discover if we apply these ideas to other mathematical problems? The possibilities are, well, pretty much endless.
And on that note, we're going to have to wrap up this deep dive. But wow, what a journey. We started with averages and ended up on the edge of like a whole new mathematical universe.
And who knows what we'll find out there.
Until next time, keep those minds curious.